is Tim Rocktäschel. I'm a lecturer at the UCL Center for AI. And I'm going to talk about the NetHack learning environment today. It's an environment that we released a few weeks ago for reinforcement learning research. It's joint work with Heinrich Küttler from Facebook AI Research London, Nantas Nadelli from Oxford, Alexander Miller from Facebook, Roberta Relino from New York University, Marco Salvatisi from Imperial College London. We do occasionally collaborate with people from Imperial College London. I'm happy to say that. Edward Graffenstadt and myself from Facebook AI Research and UCL. And maybe as a disclaimer, I should say that this is going to be a talk, as I mentioned, about an environment. I'm not really going to provide many solutions or interesting machine learning methods. I'm rather going to tell you about a lot of open research problems and why we believe that this environment is exciting to do research on. And usually when people join our group of people working on NetHack, we greet them with this meme. Welcome to the nerd zone, my friend. So there's going to be a lot of, I guess, nerdy stuff that you'll see over the next 45 minutes. We'll go much into detail about, I guess, the properties of NetHack, a game from the 80s. And yeah, I hope you enjoy that. But let's step back for a bit. So not so long ago, there was this really excellent Nature paper by DeepMind where they used deep reinforcement learning to attain human-level performance on a range of Atari video games. And this was really an inspiring piece of work. Definitely, spurred a lot of interest in deep reinforcement learning at that time. And it was impressive because their approach really attained human-level performance or exceeded human-level performance on a wide range of these Atari games. But what was also really inspiring is the fact that it worked really badly for a number of environments as well. People might know about Montezumas Revenge. This is an environment in which the approach back then didn't achieve any score. It's this adventure game where you have to control an agent, jumping around, climbing up ladders, collecting keys, avoiding enemies, unlocking doors, and whatnot. This game is really difficult for reinforcement learning because you don't really have a dense reward signal. You can only solve this game by having some exploration strategy that allows you to learn about the game, learn about the mechanics, and basically explore that via your own motivation in a way. And I think on top of that, humans, when they play this game, obviously they come with a lot of prior knowledge and inductive biases. When they see a key, obviously they expect to see a door somewhere that is locked and that can be unlocked with that key. And what was also really impressive, I guess 1.5 years ago, a team from Uber AI was able to solve this game with an approach called Go Explore. And I'll talk a bit more about Go Explore over the next minutes. So this was, again, really, really impressive. And it was impressive because previous approaches, for instance, DQN over here, right, as I mentioned, they didn't achieve any score in Montezumas Revenge. Then there was one approach called random network distillation that at least exceeded average human performance. But then Go Explore really is a big jump in terms of performance on this hard exploration game. But we should talk a bit more about the kind of assumptions that that approach makes. First of all, Go Explore makes the assumption that it's relatively easy to find a heuristic to measure similarity of states. So in Atari, you have this pixel input, and what Go Explore does, it basically downsamples that pixel input to get this lower dimensional representation that you can see on the top right. And then it uses that lower dimensional representation to measure whether that state is similar to a previously visited state. Now, once you have such a similarity metric, you can determine what are novel states, right? And you can reward the agent for reaching novel states. But this is obviously a strong assumption for many problems, it's not so easy to find a metric to calculate the similarity between states, and I'll show you why NetHack is such an environment later on. Secondly, they make this assumption that the game is deterministic. That means whenever you are in a specific state and you perform an action, and you are in that state again later on, or in a different episode, you perform the same action, it will lead to the same next state. And that assumption allows them to basically memorize sequences of actions that lead them to previously visited states and then explore from these previously visited states. They also have a variant where they even make the assumption that you can reset the environment to a previously visited state to then explore from there. And these obviously are very strong assumptions. So while it's, again, really impressive that there's this custom solution that solves Montezumas Revenge, it's, I think, very fair to say that there's little hope that it would generalize to any slightly more real-world tasks. And that's why now a lot of researchers are looking into other environments, so-called procedurally generated environments. So the difference here is that in these environments, there's a generative process that in every episode would potentially generate novel observations. One example is the obstacle tower challenge by Unity AI. It's what you see on the top left over here. So you have a 3D environment in which you have to ascend a tower of 99 procedurally generated levels. And every level, as I mentioned, these objects, they are placed via some generative process that will make sure that every time you play an episode, things will look or can look quite radically different. Another example that has been around for a while now as well is utilizing Minecraft for reinforcement learning research. Again, if you played Minecraft before, you know that every time you start a game, the world is generated for you, and there's an insanely small probability that that world will look anything like the worlds that you've seen in previous episodes. There's also a more recent example by OpenAI, it's the ProcGen benchmark environment. So these are 16 different tasks. Each of them also have a generative process to spawn all kinds of visually different looking episodes. Sometimes even game dynamics might change a bit, like the enemies that you encounter, they might have certain variations in terms of, for instance, how many bullets they can shoot and whatnot. So I think this is really exciting, right? Because now these approaches that would try to memorize certain sequences of actions to get to previously visited states, they wouldn't work anymore. Also, it's much harder to come up with a metric to determine whether two states are similar. And you really have these factors of variations through this ProcGen, this generative process that allow you to test for systematic generalization of our agents with respect to these factors of variations. So while I believe it's very crucial that we consider more and more doing research, reinforcement learning research on these procedurally generated environments, I think there's still two things that are important for such an environment. But still can run these environments really quickly. We need to be able to generate lots of experience in a short amount of time, because all the approaches that we have right now in reinforcement learning, they still need millions, if not billions of examples, right? Unless we have fundamentally different approaches to reinforcement learning that really dramatically change sample efficiency, it's still the case that in order to do research, we have to train for millions, if not billions of steps. And secondly, the environments need to be rich to drive long-term research, right? I mean, it's okay that it's a procedurally generated environment, but the question obviously is, well, what's the factor of variation? How difficult is it actually to solve a task if the only thing that changes maybe is the background color or something like that, right? Whereas there are tasks like Minecraft where there's a lot of items, there's a lot of different enemies, there's a lot of complex environment dynamics. In order to do well in this environment, you really have to learn over time about all of these things, right? You have to master basically the knowledge about how things work in that environment. So these two things are very important to me. And I would argue that Minecraft is, as I mentioned, a good example of a very rich environment where I can definitely see us building and having at our disposal a wide range of complex tasks that can drive reinforcement learning research. My problem with Minecraft is that at least right now, it's quite expensive to run, right? In contrast, OpenAI ProcGen and also the Tower Challenge, these are environments. I mean, actually, OpenAI ProcGen is something that can be run very quickly, but the Tower Challenge actually is something that's also quite slow because of the 3D rendering. But OpenAI ProcGen and also the Tower Challenge, there's actually a very limited number of objects you have to learn to interact with. So I definitely believe that these are exciting environments, but I'm doubtful whether they will drive really long-term research in reinforcement learning. So ideally, you want to have an environment that has the best of these two worlds, right? It's fast to run and very rich and complex. And we argue that the perfect candidate for that is NetHack. NetHack is a game that was originally developed in 1987. So it's a very old game. The game is run in terminal. The entire observation of NetHack or in NetHack is ASCII characters that are printed in the terminal. And it is procedurally generated. So every time you play this game, you're going to be a specific hero that has a specific role and alignment and race. It's going to be, the hero is going to be spawned in this dungeon on the first dungeon level. Every time you play this, the rooms and the corridor arrangements, they all will look different. You are going to move around in this dungeon. You might run into a door. The door might be closed or even locked. You have to walk around, collect items, for instance, food, in order to not starve to death. You can collect rings and scrolls and spell books and weapons and armors. There's really a lot of stuff that you have to learn about in order to do well in this game. But as I mentioned, it's running a terminal, and that also means it is actually extremely fast. So it's implemented in C. It's still maintained and extended in its C code base. And if you forget about deep reinforcement learning, if you just run the game itself on a CPU in your machine, you can roughly get to something like 80,000 steps per second. That's really a lot, because that means you would be able to run over 1 billion steps a day, which is a lot. Okay, so at this point you might say, well, hold on, this is a grid world. Aren't we done with grid worlds? I mean, surely we can do reinforcement learning in 3D environments and maybe even photorealistic renderings. Why should we care about grid worlds? If you are working in reinforcement learning and you've been publishing or submitting papers to machine learning conferences in reinforcement learning in the recent years and you've been working on grid worlds, you might have gotten some reviewer too who argued, well, this is a grid world, surely that's a too easy environment for me to care about, right? But I would argue actually that a lot of very exciting work in reinforcement learning actually is still being done in grid worlds. For instance, there's DeepMind's Sokoban environment. So these are extremely difficult planning tasks. There's all kinds of grid worlds. Mini grid, for instance, an example of a quite simple grid world, but still that has been used in a lot of really exciting publications over the last years. So just because something is a grid world, by no means it is an indicator that this would be an easy environment for reinforcement learning. And I hope I can convince you over the next few minutes of this, if you are not convinced about this already. So why do we think that NetHack is an exciting environment for research? Well, first of all, in contrast to Minecraft, there's actually a clearly defined goal. So you're supposed to descend the dungeon. So that means making your way down over 50 procedurally generated levels that are gradually becoming more and more difficult to master, to retrieve the amulet of Yendor, and then you have to ascend, basically going the way back to the top of the dungeon, and then you have to go even further up 5 more levels that are extremely challenging. But it has a clearly defined goal, right? I mean, once you have retrieved the amulet and you're at the top level in the astral plane, and you offer the amulet as a sacrifice to your god, and you ascend to demigodhood, then the game is over and you solve the game. As I already mentioned, so all these levels are procedurally generated. So these approaches that try to memorize action sequences or that make assumptions such as that there's a simple way or simple heuristic to measure similarity between states, they are not going to be applicable in this environment. I should also mention that the environment is stochastic. So every time you perform an action, there might be all kinds of stochastic processes going on in the background, and I'll show you an example later. On top of that, the environment is extremely rich. So there's actually hundreds of items and monster types that you have to learn about. All of them, most of them come with a lot of special characteristics and very important affordances for the items. So you really have to learn how to use them and when to apply them and when and how to not apply them, right? So this becomes extremely tricky. In fact, there's a still open debate whether there was any case in history that a human was able or is able to solve that game without consulting such external resources that tell you about how these things work. So actually humans learn to play this game a lot by consulting external knowledge sources, for instance, the NetHack wiki. Even then, people sometimes take 15 years or so before the first time that they actually win this game. The game is also extremely long. So as I mentioned already, there's like 50 procedurally generated levels down, and then there's another 5 or so up, and actually that number can vary depending on the procedure. I mean, also the structure of the dungeon is basically procedurally generated. And if you're an expert player and you've been optimizing for speed, then you might be able to solve this game in 10 to 20,000 steps. So that's really extremely fast. An average expert player, so that's somebody who still is able to win the game but doesn't optimize for speed, takes something like 50 to 100,000 steps. You can compare that with, for example, StarCraft 2. If I understood it correctly, the approach there is to perform an action or 3 actions per second. And if you then play for 15 minutes, then that's basically 2,000 steps. So we're talking about an order to 2 orders of magnitude longer episode in terms of the steps that the agent has to take in the environment to solve the game. But as I mentioned already, at the same time, it runs extremely fast. So if you employ deep distributed reinforcement learning architecture, you can get to something like 10 to 20,000 steps per second. This is really a lot because that means we can train for over 1 billion steps a day. And just to give you a point of comparison, so with the arcade learning environments or the Atari games, usually people were quite happy when they can train for 50 to 200 million steps for over the course of a few days, right? So that was basically the state a few years ago. But here with this environment, we get to 1 billion steps a day. And it's still very popular. So there are thousands of players online who play this game, who also record their plays through a shared API. And in fact, it's also open source and still under development. So as I mentioned, this game was released over 32 years ago, but there's actually still a half-year development cycle. People are currently developing a major update to NetHack 3.7. So it's really exciting to see that actually, despite the fact that this game is old, people are still developing it and playing it a lot. Okay, any questions so far? Feel free to ask me questions in the middle of the talk, by the way. Okay, so what I'll show you here is an example of an episode. So you're, as I mentioned, you're this @ symbol. You can move around in the environment. There's a pet that's accompanying you. In this case, it's a cat. You can move up. In this case, you would swap your place with the cat. And it's actually quite interesting because for many of the transitions from state T to state T+1, the game actually tells you what happened in the game. So here it will tell you you swap places with your kitten. And one interesting direction, I guess, is how to learn environment models based on also incorporating this textual information that you can see. Okay, so we're moving down. And here we run into a kobold. We are trying to attack the kobold. And as I mentioned, this is a stochastic environment. So every time we perform an action, there might be in the background actually a die roll to determine the outcome of our action. So it's similar to Dungeons and Dragons, if you're familiar with that. So then the kobold hits us, we hit it again, we kill the kobold, we move further around, and then we reach this door over here. The door is closed. We open the door. At this point, you see that NetHack also has this kind of simple light model. So here we see that we can only look into some part in the room. Once we enter the room, we see the entire room. And here's now an interesting case. We have a locked door. If you don't have an unlock tool like a lockpick or a credit card or a key, then you're not going to be able to open that door, but you can still kick it in. So one action or one possibility, as I mentioned, is kicking. This is actually a composite action. So you have to say you want to kick, and then you have to select a direction to then kick the door. In this case, the door is still locked. If we kick a bit further, we might be able to then kick in the door. It crashes open. NetHack has a lot of actions. So actually the action space is something like, I think 170 different actions. Very few of these actions actually allow you to also enter freeform text. So you could, for instance, name your pet or name certain items. For reinforcement learning research, I don't think that's really important. But still, you have a big action space of 170 actions, some of which are compositional, as the kick action that I just demonstrated. What's also interesting is that the kick action is, so we thought, is a difficult action to learn for a reinforcement learning agent because it's quite hard to explore that action. First of all, because it's compositional, right? You have to kick and then kick in a specific direction. But also because if you kick against the wall, that might actually break your leg and it might lead to you losing health points. You might even die from that. So it's actually a very costly action to explore. But we'll see later that at least right now, vanilla deep reinforcement agents are actually able to master this action. Okay, so then sometimes you run into these dead ends, and there's another important action, which is searching. So throughout the game, you find yourself in situations where you don't see any way to progress, and then you have to walk around search to find hidden doors, secret passages, and whatnot. Again, that's a really difficult action to learn, so we thought, because oftentimes it's not sufficient to just search once. You might have to search 10 times, 20 times. You might have to even walk around a room to search all the walls, whether there's a secret door to be found. So we thought that's actually quite difficult to learn through random exploration, but as we see later, this actually still works out for distributed deep reinforcement. Okay, so then we're kicking in that door, we're exploring a bit further. Here we see a staircase down, we go to a staircase down, and now we are entering the second dungeon level. Again, everything is procedurally generated, so we have no idea in advance how the room layouts will look like. We find another staircase down, and now we are entering a different part of the dungeon. This is the Gnomish Mines. They will look very different from all the rooms and corridors that you've seen before. It's actually a more open plan office in a way, and that there's no separation of rooms, and that obviously has consequences for the kind of policy that you should be applying in order to not get swamped by enemies. Anyway, so you might not characters. There's actually by now also various graphic user interfaces to NetHack, for instance, in this isometric view, or you can even play this in the browser nowadays. So if you are inclined, right, you might want to learn or train reinforcement agents based on that visual pixel input, but at least in my view, there's not really a point in doing that. In a way, you will just waste a lot of samples in order to understand these visual inputs. You might as well just work directly on the ASCII characters, treat them as symbols, and learn from there. That's at least what we do. Okay, so as you already, I guess, noticed by now, I'm talking a lot about NetHack, the game itself, but I promise we'll also get to some reinforcement learning results. But before that, let me just really convince you about the complexity of this game. There's one example that's really excellent that's taken from YouTube by Mr. Wendell. He explains the situation in the game where you are facing off with Medusa. So this is Medusa's island over here, and it's surrounded by water. The problem is that water rusts and corrodes your metallic items, such as weapons and armor. So that's really bad because then they become much less effective. So you really want to avoid that. Also, when you step into water, there's a chance that you might drown and instantly die. And as it's common in these roguelike games, once you're dead, you're dead. So that means you really have to then start the entire episode from scratch. And like hours of gameplay might be lost as soon as you die. But you can apply a can of grease to prevent rusting and corrosion. You can also apply a can of grease to a bag or sack, and that will actually turn it into a waterproof container for items. So then you can put all the items that shouldn't get wet into that container. Things like, for instance, spell books and scrolls that otherwise would be erased. The sea or the water here, that can also contain a kraken, and if that kraken grabs you, it can drown you almost instantly. So that's another source of a really stupid death that you would want to avoid. Well, you could also take a can of grease and grease the hero's armor, and then that would prevent the kraken from grabbing you. And once you reach Medusa's island and you're in line of sight of Medusa, she will petrify the player, which again is a source of instant death that you want to avoid. You can, if you have one, you can apply a towel to cover the hero's eyes that would blind the hero, and then it allows you to play to fight Medusa without getting petrified. If you happen to have a mirror with you, you can even petrify Medusa with your own gaze. So hopefully this gives you some glimpse into complex environment dynamics that you have to learn to master in order to do well in NetHack. So now, what is the NetHack learning environment? It's basically three things. It's a gem wrapper around the full game of NetHack. So you can actually play the entire game of NetHack through that Python interface. As I mentioned, it's extremely fast to run. It's also a bunch of tasks, because we strongly believe that solving NetHack, meaning actually being able to descend to the bottom of the dungeon, retrieve the amulet, and ascend again, that's going to be extremely challenging. And it probably will take years until we see any approach being able to solve NetHack. But on the way, there's already a lot of subtasks that you have to master. And we, in the release of the NetHack learning environment, we provide an initial set of these tasks that people can use to train reinforcement learning agents. It's also extremely simple to add even more complex tasks to this environment. So the first task is to, on the first level, find a staircase down. That's already challenging because you have to, as I mentioned, learn to kick in doors, to search for hidden doors and hidden passages, and also avoid all kinds of traps. Then there's a slightly harder variant of this version where you have to find a staircase, but you need to be accompanied by your pet. The pet is controlled by the environment itself, and it moves stochastically around, but it also follows the player if the player is not running away too quickly. But then in this case right here, you also have to make sure that the pet survives and doesn't get lost and doesn't get trapped and whatnot. Another task is finding gold. Gold is important in the game because you can use it to trade it for items with shopkeepers. Finding gold works by collecting gold that's lying around in the dungeon, or through quite advanced strategies that, for instance, involve killing shopkeepers or finding gems in the gnomish mines and selling them to shopkeepers and whatnot. In NetHack, it's difficult to even stay alive for a few thousand turns, because over time the hero will get hungry and potentially starve to death. So this task rewards the agent every time the agent finds some source of nutrition and consumes it. There's another task where the reward function is basically just how much of the entire NetHack dungeon have you uncovered. So every time you enter a new room, you would get a reward, or every time you find a new passage, you would get a reward. Another task is finding the Oracle. So that's extremely challenging. The Oracle is a specific room that's spawned somewhere between level 6 and level 9. And finding that is difficult because that's a really sparse reward setup, right? So you're only getting a reward when you're standing next to that Oracle. Lastly, another task we propose, which I think is quite important, is trying to just maximize the in-game score. So NetHack actually does provide you with a score that somewhat measures progress in the game. So it, for instance, increases every time you kill a monster, every time you descend further down in the dungeon, every time you learn something about the scrolls and spell books, when you identify objects. That's cases where you get in-game score. And yeah, you can try to maximize that directly. The problem is that it's not really giving you a good learning trajectory towards actually solving the game, because it will mean your agents are way too aggressive, right? They just try to kill everything in their path and they try to descend as quickly as possible. That's not really a good strategy for long-term survival. But still, if you had an agent that would go quite far in the game, it would have a quite high in-game score. So I think it's a good way to measure progress of methods while we are not yet solving NetHack, basically. Okay, so when we released this, there was I guess Gideon Mann from Bloomberg said, well, also you can run this in Emacs. Actually, yes, you can. I tried this out. So this is my Emacs setup. On the left, I instantiate the gym environment. On the right-hand side, I actually execute the OpenAI gym environment within my Emacs. So that works if you fancy it. The model that we release with the environment is very simple, standard deep RL setup. We have the entire dungeon map. As I mentioned, it's represented as a matrix of symbols, of ASCII characters. In fact, it's not the ASCII characters. There's actually many more symbols than there are ASCII characters. So if you have a specific symbol like this percentage sign, it tells you that this is a food item. It could be a monster corpse. It could be one of many food items. If you inspect the food item, you would know what it is. But from just looking at the map, you don't know that. We're actually using the underlying so-called glyph representation. So this is actually a unique ID for every possible different entity in the game, of which there are in total 6,000. And we map each of these symbols in this matrix into a dense vector representation using a lookup table. So it gives us this tensor of height of the dungeon, width of the dungeon, times the dimension of our latent symbol representation. And then we run a convolutional network over that entire tensor. We have another similar setup where we also take into account a egocentric view around the agent, and again do the same thing. We embed all of these symbols using a lookup table, and then we run a convolutional network or transformer over this. And there are a lot of different agent attributes that we also incorporate using a feature vector. So as I mentioned, this trains for roughly 10,000, or if you use a transformer, 5,000 steps per second. That means you can train this 400 million to 1 billion steps a day. Each of these different, if you want to call them modalities, would end up in a different dense vector representation, after which we then have a fully connected layer, or 2 fully connected layers to map that down into a shared representation, which then is fed into this recurrent policy learner, to this recurrent policy that then spits out the policy logics. Also, by now, we're not making use of these in-game messages, but I think that would be a really interesting direction to follow. So that's the convolutional network baseline. We also have another variation where we, on top of the convolutional network, employ random network distillation. I'm not going to spend too much time on this, but basically, the idea is to have the original network, and then have a copy of that network that's randomly initialized and that stays random. And then during the course of training, you measure the discrepancy between what your random network predicts and what your actual network outputs. And that discrepancy you use to generate intrinsic reward. And that's a very robust approach, and can also be applied not just to Atari, but also these grid wells. Now in NetHack, I mentioned it's procedurally generated. There's already a lot of variability, but it's actually even more dramatic than that. A lot of environment dynamics are conditioned on what kind of character class or race or alignment you use. So there are 13 different rules, 13 different roles, such as barbarians, knights, wizards, Valkyries, and whatnot. 5 different races, humans, elves, gnomes, and whatnot. And that gives you a quite big space of possible characters to explore. And as I mentioned, you know, if you are mastering one of these characters, doesn't necessarily mean that you find it easy to play a very different character. So it's quite similar to the setup, I guess, in Dota, where depending on the character, you have to learn quite different policies. So we train agents as a monk, a Valkyrie, wizard, and tourist with different, I guess, alignment and race and whatnot combinations. Okay, so let me tell you a bit about the results. So as I mentioned, I guess these are very simple baselines. So the convolutional network is definitely a very simple baseline. R&D, as I mentioned, is a quite common exploration technique. And we wanted to see basically how far can you get in the game using these quite standard approaches for deep reinforcement. And first of all, let's focus on the staircase and pet task. So these are, you can see them basically as unit tests, right? So these are really relatively simple tasks where if your approach is not able to make progress on these very simple tasks, then clearly something is going wrong. And what we see here is that, first of all, there's a large difference depending on what kind of character class you use. So certain characters, as I mentioned, certain roles that are much easier or much harder to play than others. We do see improvements of using random network distillation. So the yellow and the brown line here, these are the Monk and Valkyrie with the random network distillation for exploration. The baseline without exploration bonuses, so the gray one and the blue one don't achieve the same level of performance, so they're less sample efficient, also generalize not as well. In the pet task, you see relatively similar picture. Also note that this is a much harder task, as I mentioned, because you have to take care of your pet. Maybe slightly more interesting are these open-ended tasks. So as I mentioned, score and explore or scout. These are tasks where here you would maximize the in-game score. Our agents, again, with random network distillation, they get to roughly an average of, well, here 750 in-game score. That's already quite good. So if you haven't played NetHack before and you start playing this right now, I would be quite impressed if over the next days you can reach to a level where you consistently get 750 or more, well, on average 750 in-game score. We also have a analysis that tries to investigate how strongly can we generalize as a function of how many different seeds do we use during training. So as I mentioned, in these procedurally generated environments, there is a generative process, and that generative process that creates the levels can be seeded. And you could, for instance, fix that seed, right? You could say in every episode is going to be the same seed. And what you see when you do that is that, for instance, for the score task, remember previously results were at around 750. If you fix the seed, then actually we get to a much higher score, right? We get to 1,400 on average, or with 10 seeds even 3,000 something, because with this one seed, apparently we got a bit unlucky. But this is much higher than the score that you saw when training on all seeds. But at the same time, if you then test on unseen seeds, so 100 randomly sampled unseen seeds, you basically see that the agent isn't able to do anything. You get a score of almost close to 0. And that really shows you that if you train on few seeds, right, you basically don't have agents that can generalize at all, right? They might be good at the specific seed that you provided to them, but if you then test it on slightly different slightly different circumstances, these agents won't be able to do anything. And if you want to be cynic, right, then you would say, well, actually, this is the Atari setup, right? Here, if you train Montezumas Revenge, that's basically just on one kind of Montezumas Revenge. There's no variability between different episodes in Montezumas Revenge in that regard. So while you increase the number of seeds, first of all, observe that the training performance goes down. So that's an interesting expected observation. It's interesting because it means there's a specific point at which the model, although it's a very capable deep function approximator, is not able to memorize the specific properties of the given seeds. So at some point, actually, both the training and the test scores collapse to the same point. So for us, it happens at around 1,000 different seats. That was also the case in, I think, OpenAI ProcGen benchmarks results, where they did the same analysis. But while the training performance goes down, the test performance actually goes up, and you get agents that can generalize to unseen seats. Okay, so one thing I want to mention is that given that NetHack has the symbolic observation space, all of these ASCII characters, it's very easy to track all kinds of metrics about how these agents do in the environment. So for example, we can track how, during the course of training, how deep the agents descend into the dungeon. So in our case here, to roughly 4.5 dungeon level depth. You can also track how many experience levels they level up and how many steps they set in the game before dying. And to us, that was really useful in order to debug and analyze our agents. You can also investigate whether your agents are able to kick indoors, whether they did starve to death, or whether they got killed by food poisoning. So if you just look at this plot over here, this is basically telling you what's the proportion of agents that are dying because of starvation as during the course of training, right? So you see, for instance, for the score goal task, that maybe a fourth to a fifth of the agents in the beginning of training, they die of starvation. As training continues, that goes down, but at the same time, they then start to die more from rotted corpses. That means they kill enemies, they try to eat them to not starve to death, but then occasionally they let these corpses lie around too long, so they become rotted, and then because of the way NetHack works, you would then die from food poisoning when consuming these corpses. We can measure progress in terms of the dungeon. Our best agents, when they get lucky, they might descend to depth of 10 or 11 or 12 or so, but there's still a really long way to go. So from this picture, maybe it looks like we are 10% done or 20% done with respect to the game, but actually I would argue it's probably more like 1%, because the further you go down, the much harder this becomes. We also see agents passing by landmarks such as the Oracle, Gnomish mines, Mine Town, and so on. So this is quite encouraging, but again, they find it actually quite difficult to reliably navigate to these landmarks. With the release of the NetHack learning environment, we also open source the dashboard, so that allows you to load all the episodes during training, look at specific statistics about these episodes, and even replay these episodes so that you can analyze qualitatively what's going on in the environment. Let me just give you an example of a trained agent. So this is one of our agents. I think it's a monk trying to maximize in-game score. It learns to navigate the dungeon relatively reliably, navigating to these staircases down, killing monsters on the way. At this point, it's already in the Gnomish mines, starting to kill a lot of monsters there and trying to find further staircases down. So yeah, basically, as I mentioned, we were quite surprised at how well relatively standard deep distributed reinforcement learning approaches can already allow agents to navigate these dungeons. And here, in this case, the agent's now at level 5, passing through Mine Town, killing a lot of monsters there. Okay, I'm going to skip that. Maybe one thing to mention as well. So this is a screenshot from a server on Oxford where people are playing NetHack or have been playing NetHack decades ago. There are some famous people at the top of this leaderboard. So this is Philip Tor, professor at Oxford, who has been ascending to demigodhood 5 times. There are other professors on this leaderboard as well. Professor David Forsyth, he got to, I guess, a score of 4,000. So our best agents right now, when they get lucky, they also get to a score of 4,000 and higher. So we definitely beat David Forsyth. And at the bottom of this leaderboard, at least, there's Anandas Nadelli, PhD student in Oxford, who, didn't do really well. And what I found quite impressive is, I guess, how well this in-game score correlated with the academic rank. So maybe that tells you something about professors spending too much time on NetHack. I'm running out of time, but I just want to very briefly sketch research directions in NetHack that I'm interested in. Obviously, you can do a lot of things. You can use NetHack for learning from demonstrations. You can You can investigate hierarchical reinforcement learning, model-based reinforcement learning, planning, and whatnot. But the two things that at least I'm quite excited about nowadays is curiosity and exploration. When humans learn to play NetHack, they don't use whether or not they won the game as a reward, right? Because it takes them years to win this game for the first time. They are motivated by many other things in the environment. I think one of the driving forces is, for instance, just learning about the environment dynamics, learning about how things work in NetHack, expanding their knowledge about the different items and what you can do with them. And we are working on different approaches to model that kind of curiosity for deep reinforcement learning agents. The other direction that I'm very excited about is how can we go beyond this tabula rasa learning approach where you train a deep reinforcement learning agent from scratch, and all the experience that the agent gathers within the task environment is enough to do well in the environment. How can we go beyond that and condition reinforcement learning agents on external, based on external knowledge sources such as wikis, the text there, and also the tables and info boxes in these wikis. So Jan LeCun had this, I guess, cake metaphor where he was saying, well, reinforcement learning, you can forget about this because that's really just a cherry on top. You get this scalar reward signal once in a while. That's really not enough information to learn from. Really what we should be doing is supervised learning, or actually unsupervised learning. That's the actual cake that we should be caring about. But I would argue we've been maybe, while I agree with this, I think we've been also looking at the wrong cake. I think the cake I care about looks a bit more like this, where you have a lot of knowledge that we as civilization gathered over the last hundreds of years, and that's written down maybe in textual resources that we should be learning to leverage. So it's a bit like, I guess, Neo in up to machine and then says, well, I know Kung Fu. So if you're interested in that kind of direction, we had a paper at iClear this year, which I don't have time to talk about much, but it's a paper where we present both an environment and a solution for generalizing to novel environment dynamics via reading. And I think while that might have been basically a very small cake because the documents we were conditioning on were very short, I think now it's really an exciting time to go large scale, to look into really humongous cakes. And with those, I mean basically Wikipedias, right? So for NetHack, as I mentioned, there's a really large Wikipedia that tells you about all kind of things that you need to know about in order to do well in NetHack. It would be really great if we could somehow hook that up with our deep reinforcement agents. As I might have mentioned, this NetHack wiki contains over 35,000 pages, of which 3,000 have content. So really how to learn to utilize that textual knowledge, I think, is extremely important going forward. And I think there's reasons to be very hopeful. Patrick Lewis is a UCL PhD student. He just released, I think last week or 2 weeks ago, a paper on retrieval augmented generation for knowledge intensive tasks. So this piggybacks, I guess, on all these advancements of pre-training language models and pre-training language representations, but goes a step further than that. It's also hooked up with a retrieval mechanism to find very specific relevant information in the entire Wikipedia in order to solve downstream tasks. And it's then trained all end to end. The other direction, as I mentioned, I'm excited about is how can we imbue agents with intrinsic motivation and curiosity. We had a paper at iClear this year where we developed an approach that's specifically robust with respect to procedurally generated environments. So if you're interested in that direction, please have a look at that paper. Okay, so with that, let me summarize. So the NetHack learning environment strikes, in my view, a really fantastic balance between complexity and speed for deep reinforcement learning research. As I mentioned, it's procedurally generated. Agents cannot rely on memorization. They have to systematically generalize. There are really a lot of entities and interactions between them that agents, as well as human players, have to learn about to master the game. We do see some progress with standard distributed deep RL baselines. And as I mentioned, the two promising directions are conditioning on external knowledge and curiosity-driven exploration. It's open source, so if that's relevant to your research, really, please try it out. Give us feedback of how it works for you. And with that, thank you.